In this video, we're going to work an example problem where we view the meaning of a Taylor series from a different perspective. So what we're going to do is we're going to find the Maclaurin series of this function using any method we want. So we could use the definition of the Taylor series definition, or what we're going to do is we're going to reference, use e to the x, the Taylor series for e to the x, the Maclaurin series specifically, as a reference. And then once we have that, we're going to write out the first 3 or 4 corresponding Taylor polynomials of that series. So like that would be the t sub 1, t sub 2, so that just with one term, and then adding 2 terms, adding 3 terms, and plot those along with the Taylor series, plot those graphically to see how the Taylor polynomial as n gets larger and larger, it's converging to the Taylor series. So that's another way. You have the definition of the Taylor series from the standpoint of the c sub n, right? Is equal to 0 to infinity. Here's a power series, c sub n, x to the n, or x minus a to the n, but that c sub n that's one definition of a Taylor series. But another definition is, so this is, you say that that's the Taylor series, right? And that usually the function is equal to this. But another definition is you have a Taylor polynomial, which is, so t sub n of x is, you change this to the format where instead of going to infinity, it goes to n. So, and you do that, remember we learned about this in the first half of the chapter. With any series, you do this by, you change the n variable, the n, each n from n to I, so that you could, instead of putting infinity up here, you could put n up here. Okay, there's the Taylor polynomial, so you choose n. And in which you're left with not the infinite series, but the first n terms of the infinite series. And another way of viewing the definition of the Taylor series is that the Taylor series is equal to the limit as n approaches infinity of t sub n of x. So this is the definition we're wanting to take a look at in this video. And, again, just a reminder, in the first half of the chapter, we did all kinds of convergence testing, and also we did partial sum problems and then, estimating the error of the partial sums. But those, it's the same concept here, but there was no x involved. So we had from n is equal to 0 to infinity of just an a sub n, where there was no x's. But it was the same concept in that you could, this was s. But if you could find a actual s sub n formula, so in other words, so like s sub n, the partial sum, you change the n to I, so you could put n here and just change this instead of a sub n, a sub I. You could always write, as long as you had an a sub n, a summation, you could always write the s sub n like this, the partial sum. But if you could actually find a partial sum formula, which we could do like we did for the geometric series, for example, then you could take the limit as n approaches infinity of that actual formula and see if the series converges and what it converges to. Or if you couldn't do that, then you could use the partial sum formula to get and go to n is equal to 10, 20, and then get an estimation of the infinite sum. And that's where, so the same definition of s, you could write it as, this is equal to the limit as n approaches infinity of s sub n. So it's the same concept. But it's also remember, when we were calculating s sub n's, that's where the definition of r sub n comes from. S, the infinite sum, is equal to the partial sum plus the corresponding remainder, r sub n. And that's where you could do the same thing here. The Taylor series is equal to the nth Taylor polynomial plus r sub n of x. This is the same exact concept, but just now we're working with these power series. And the r sub n of x, we use that for, in the next section, we're going to use this to calculate the accuracy of a Taylor polynomial. But we also use that in this section to prove that a function was equal to its power series by proving that the limit as r approaches infinity of this r sub n of x is equal to 0. With Taylor's inequality, we were able to find an r sub n of x, assuming that the function is equal to the Taylor series. We would make that assumption, and with that, we were able to find the corresponding r sub n of x, and then we just need to prove that the r sub n of x, the limit as n approaches infinity of that, was equal to 0. Okay, so there's the background on the Taylor polynomial and how it's associated with the definition of the Taylor series. So let's go ahead and get this Maclaurin series representation for this function. So, okay, we're going to use e to the x as the base series here. So that's the sum as n goes from 0 to infinity of x to the n power over n factorial. Okay, but we've got e to the minus x. So, okay. So we've got x out front, and then we're going to substitute the minus x for in place of the x. Okay, so this is all right, minus 1 to the n. We could take out the minus 1 to the n, and then we've got x to the n times x to the first, so that's x to the n plus 1 over n factorial. So let's do this. Okay, so there we go. That is, so we've got x e to the minus x okay, so there is the Maclaurin series of the function. Now let's also get the radius of convergence, because we'll have to consider that in the plot. So okay, we'll do a sub n plus 1. Okay, the minus 1 of the n goes away. N plus 1 is n plus 2, so x to the n times x squared over n plus 1 factorial is n plus 1 times n factorial times, okay, n factorial over x to the n times x. All right. So we've got, we can bring out this. There we go. So the limit as n approaches infinity of this is equal to, this goes to 0, 0 times this is 0, so this is 0 for all x, which is always less than 1, so this radius is equal to infinity. Okay, so now, you know, we remember that this is actually, these two are equal. We don't have to prove these are equal. So, and for actually plotting this, we can just plot this function. Okay, this is this is the Taylor series. Okay, this is t of x. Okay, so now let's do, just to make this interesting, instead of doing like the first 3, like n is equal to 1, 2, 3, let's do, so maybe, so t sub 2, let's do that. And then maybe we'll do t sub 4 and t sub 6. Okay, so when n is equal to 0, we've got what? Minus 1 to the 0 is positive 1 over 1. It's just x. Okay, then it's going to be minus, and then you've got 1 factorial, so then just x squared. Okay, that's t sub 2. Now t sub 4 is going to be x minus x squared, then plus, okay, minus 1 to squared is positive 1 over 2 factorial. So 1 over 2, and then x cubed, and then minus, it's going to be 1 over 3 factorial x to the 4th. Okay, t sub 6 is going to be x minus x squared plus 1/2 x cubed minus 1/6 x to the 4th plus, okay, so 1 over 4 factorial, 4 times 3 is 12, 12 times 2 is 24, then x to the 5th, then minus 1 over 5 factorial is going to be 120 x to the 6th. Okay, so what we want to do is we want to graph each of these along with this function, the actual Taylor series. Okay, so this is the Taylor series in red, and then blue is t sub 2, green t sub 4, purple t sub 6. And the red comes down, it's like behind the purple and the green, but you can see that, so t sub 2 is here, and then when you go to t sub 4, it's starting to, especially in this region, it's really coming on top of the Taylor series. But as far as in the positive x region, you go from t sub 2, t sub 4, t sub 6, it's coming out like that. And so, you know, if we kept increasing, you could just imagine, so even up here, right, it's starting to hug the red curve even more and more. And as n goes to infinity, it would eventually, the Taylor polynomial and the actual Taylor series would match.